Okay, I have a question for you. What country did Tom take this picture in? Anybody? Ireland, that's right. This is in the Bruin in Ireland. Okay, I've got another question for you. How many people in here, raise your hands, know how to dial a dial phone? Have done it a lot, pretty much. Okay, not everybody, but a very large number. So we're not the kids' generation here yet. Okay, that's good to see. Now here is a picture. So I want to ask you, with this dial, do you know why if you dial the 0 or say the 9, you have to go all the way over and then lift your finger and let it go all the way back before you do the next one? Do you know why? Okay, I'll show you. So here is a picture of Tom's neighborhood. Now this is local Google Street, so maybe if you take a look at this, here's his house right there, okay, see that? And his school, and this was more woods. I don't think the tennis courts were there. And right over here, what's that? That is a telephone exchange. And the difference between the two is maybe a kilometer, something like that. And over in his house, at least for many years, was one of these dial phones. Now, what was in this red building? This is what it looks. So when he was a Boy Scout, in elementary school, he took a tour of that red building only once, and he was amazed because this is what he saw. That is the phone, the 9 or the 8, sending that many clicks to electrical mechanical relay, which establishes connections and sends it through the PBX to the next. That's how they worked. No computers, none at all. And they were very reliable. And in the US, about the time when he was living as a kid, there were this many of those buildings in every neighborhood because you had to be pretty close to one of those in order for your phone to send the signal through for every single digit and get the dialing right. So that's where he lived, in Milwaukee. Now here's another picture. This is the broadband network in the early 50s, 54, 55 time frame in the United States. By broadband, I mean relay towers that did line of sight transmission of stuff with microwave relays. And right here, not actually in Lake Michigan, a little further to the west, is one of the relay towers called Slinger. And here is a picture of that tower, and you can see right here, radio tower. So these are mile squares in here, and right here, that lake is on the property that my father bought when I was a young child, maybe 8 or 10 or something like that. And here's the house that we lived in summers for quite a few years, not a kilometer from this nice radio tower. And in that time, lots and lots of phones got switched very reliably with no computers behind them. If you go on to 1967, so this is the first time I've ever given out this date. This is my first job after I graduated from college. So, you can do the math. I was doing reliability software, and I didn't actually remember that I would have called it that until I had to put together a talk on reliability engineering because I stuck my neck out and said it was a good topic. And so I was working at Bell Telephone Laboratories in Naperville, Illinois, and I was working on the number 2 ESS, or electronic switching system. And this was the number 2 because number 1 was a bigger one. It was first deployed in 1965 in Schenectady, New York. And the number 2 ESS was deployed in, I believe, 1970, a couple of years after I was working on it, near Naperville, Illinois, where the branch of Bell Labs was that was working on it. So this is what it looked like. Now, the number 1 had very discrete components. This particular one had actual boards with little tiny sort of like integrated circuits on them, but you know, they'd pull in and out with pins. And it had lots and lots of discrete components. Here's some resistors and things like that. The design goal for this computer, for a community modest size, you know, suburban type of exchange, was the cost to install and the reliability had to be equivalent to the existing electrical mechanical systems, which you just saw. It had to be just as reliable. Once it was in, you could start putting push button phones in because it could actually recognize the dial. And so that meant that, and we had this drilled into our heads from the day that I entered the building, was the goal was a maximum downtime of 2 hours in 40 years. And I'm thinking, I don't even think it lasted for 40 years. But if you take a look at that, that is 3 minutes a year. So does anyone know what 5 nines is? 5 nines is 5.5 minutes a year. So this is better than 5 nines design goal for discrete component computer with components failing all of the time. I mean, they knew the mean time between failure of all of the components. They could calculate how often they would fail, how often they needed to be replaced. And they put together a system that looked like this. So what you have here is, here's your switching network, and then you have 2 programmed central processors, 2 input outputs, here's your program information, here's your call store, and then down here to some alarms and some down here typewriter. So that was the architecture, and the system worked like they continually looked at each other for a mismatch. If there was a mismatch, by some magic that I never did understand, it decided which one was bad and isolated it. And then my job was to go through and run diagnostics on the isolated cards to isolate the fault in the computer that had been kicked out to a particular card. And then I would print out on the teletypewriter which card. Maintenance guy would go in and swap it out pretty quickly because, of course, you could only have a computer out for, you know, 1/2 of the processor out for so long if you were going to hit your downtime design goals. And so the way I tested it, for example, was I would like pull out a little transistor or pull out a card and see if my software could detect it. It was a lot of fun. It was an interesting set of, the language that I used was a register shift language that was designed by a senior woman who was one of the top software engineers at Bell Labs. Did it work? Well, I read an IEEE article from the project manager who said, yes, it met its design goals. And it probably did. But then again, in 1990, we had this little incident where more than half of AT&T's networks crashed after a switch at a switching center, one of those switching centers, suffered a minor problem, shut down the center. When the center came back, does this sound familiar? Center came back up, sent messages to other centers, causing them to trip, shutting down and reset, and it continued around the country for about 9 hours. So that's not really meeting your 3 hours in 40 years, or 3 minutes in 40 years. The culprit turned out, would you believe, to be a little tiny bug in one line of code. So we've heard this story before, so it didn't quite meet its design goals, but the fact is, except for this incident, it did really well. The reliability of landlines, the fact that they're not powered from the electrical system in the house, and they're all running underground where the signals go very reliable, has been legendary. And there's disasters, there's floods, there's tornadoes, whatever. Generally speaking, landlines have stayed up while virtually all other types of communication have gone down. Not always, but they've been very prized for their reliability. So that's what I did first, and it was flat out reliability software. The next, it wasn't the next job, but a couple jobs later was equipment control software. I was working at 3M. Now 3M makes tape, yes, Scotch tape, masking tape, you name it. And this is the kind of process that we were controlling. It goes with a clear plastic, you put a coating on it, and the fun stuff that we were doing, I think you'll see it in just a moment. this is what we call the beta gauge. You can see there's a little radiation thing on it. And what this did was determine the thickness of the coating so that we could change the thickness at which it was being spread so that it came out really evenly. And these rolls are 54 feet wide, so they're great big hunking things. And they're running usually in an explosion environment, so if you have any kind of spark from one of these new things called a mini computer, it could do bad stuff. And this is pretty much the tape making process. And I spent a lot of time, quite a few years, putting together control systems for these processes. The control software I learned, because I was in an engineering department as opposed to a IT department. I was in our control engineering department. And the first thing we always knew was it had to be reliable. Well, what did that mean? First of all, it meant trustworthy. It had to work the way it was supposed to work, the way it was expected to work. And that wasn't according to spec, it's according to the way the operators in the plant kind of would have expected it, which meant we typically had to talk to the operators and find out what they expected. It had to tolerate faults because there's no way that this particular set of equipment can be guaranteed to always be up. It's just not going to happen. In fact, all equipment always fails, just a matter of when. So it had to make sure that we couldn't let it fail in a bad state, because if you think about those giant roll good processes, all you need is one to run away on you rather than stop when something goes wrong, and you've got a huge mess, if not worse, on your hand. And so always it had to fail safe, and in addition to that, we had to contain any damage, which is currently called limit the blast radius, to a small area, which we did generally with very modular designs. One thing we knew for sure was that safety was a primary concern, because these were big equipment, pieces of equipment that if anything fell, it could really hurt or kill somebody. So when I put my computers there, because most of the guys did all this stuff in wires, the senior engineers would put like emergency stop systems around my code and say, yeah, you can do whatever you want, but we're going to do the emergency system and make sure that if anything goes wrong, our stuff is going to stop it. So that reminds me of this guy here, because my son is a civil engineer, actually in environmental engineering, and he called me really, really, really upset about 3 weeks ago, because he said, how can any engineer write code that doesn't do dual input and checking across two inputs, doesn't do any kind of redundancy, and consider themselves or ever call themselves an engineer? I said, but, and he said, no buts, because when I was teaching, he taught civil engineering students, the first thing they learned was that safety is the primary responsibility of an engineer, a structural engineer. And in fact, the code of ethics of professional engineers says that they have to hold paramount the safety, health, and welfare of the public, which means that they must understand how what they're doing fits into the overall scheme of things and might compromise safety, and call it out or fix it if that happens. So I guess he had a point. And I'm especially concerned because this is what's going on these days. This is a list of all of the computerized control systems in a car today. And this isn't even automated driving. These are just systems that have various types of software behind them. And it's a computer on wheels. Are we thinking really hard about the whole concept of safety when we put together any kind of software that's going to be in any kind of a control system? So that's another kind of software than the software I was doing at Bell Labs. But I want to talk about when you have complex systems, the kind that you deal with, what kinds of failures tend to happen. So let's talk about July 8th, 2015, because at that point in time, the stock market was suspended trading for 4 hours due to what turned out to be a configuration issue, whatever that might mean. At the same time, the very same day, a quote-unquote faulty network router brought United Airlines down for 2 hours and basically messed up their schedule for the next 24 hours. At the same time, the Wall Street Journal main page had this, oops, 504. And there were people who thought the world was coming to an end with all these three things happened at the same time. So if you take a look at December 17th, 2017, there was a fire. Okay, fires happen, yes. This was an electrical fire. And the busiest airport in the world, Atlanta, was shut down by a massive power outage in a tunnel underground, caused by an underground fire. So lastly, I want to talk about a backup switch failure blocked 52 million Visa transactions in Europe on June 1st, 2018. That might have affected some of you guys. The point is that these are not software failures. These are system failures. The whole entire system. And don't care how perfect you think you're going to get your software, there's still going to be stuff that happens. Stuff happens to fires happen underground, routers go out, stuff happens. So if you take a look at the whole system, reliability is not a software characteristic, it's a system characteristic. And there is a very interesting paper that was published in 1988 called A Case for Redundant Arrays of Inexpensive Disks. Now, RAID right now doesn't use inexpensive, it uses independent. But this was the very first paper on the whole concept that tiny little disks were better for storing more data and more reliably than great big massive central CPUs. 1988, in fact, the paper was so groundbreaking. They were looking for how do we store the most data in any kind of database, and they found that the gating factor happened to be writes to disk. Well, if you have a lot of disks, you can write a whole lot more more quickly. So the paper that was under review got widely distributed, and before they even got it published, there were whole bunches of vendors calling saying, whoa, this is a new idea. Now, I didn't actually hear about it till more like 1999. This is when Google got this concept of lots of little tiny disks way before most of the other Silicon Valley companies. And this is when they started running Bigtable in Stanford lab, because that's where Google started up. And this is from the Computer History Museum. That's their first big rack of stuff. That same year, they hired these two guys, Jeff Dean and Sanjay Gemwat. They were working in a DEC research lab nearby, and this was, sort of children of the person who started the Palo Alto Research Center. It was all pretty close. And these guys were working at the DEC Research Center, and they got hired over to Google, and they became responsible for the core infrastructure, because Google had this crazy idea that they wanted to search all the information out on the web and make it rapidly available to people, and nobody really had a clue how you put together the infrastructure to do that. These guys figured it out. Jeff Dean said, ultimately, it was frustration with being one level removed from real users using my work that led me to go to a startup. Think about that. The really powerful engineers would like to do something useful close to users. And so they were very involved in figuring out. In 2003, they published a paper showing how they did their Google file system with little tiny bits of pieces all over. And in 2004, the MapReduce paper came out showing how you could search in place. And pretty much that's how the internet works these days in many levels. So Jeff Dean said at a speech in Lattice, that's the large scale database or something conference, he said, things are going to crash. You're just going to have to figure out how to deal with it. And how they dealt with it was this concept of redundancy and limiting the blast radius to a small area. In 2003, Ben Trevor joined Google to lead a team of software engineers, because by this time, they were getting to be pretty big, and they were getting to have a lot of crashes, and they were getting to have, their infrastructure was okay from an engineering point of view, but not necessarily as reliable as they thought. So they hired Ben, who happened to be a software engineer, and said, figure out how to keep our production environment up. So he calls site reliability engineering what happens when you get a software engineer and tell him to keep a bunch of hardware working. Instead of what was the policy at the time, lots of sysadmins, lots of manual work, that sort of thing. What he talked about was figuring out how to automate the management of all of those computers. The goal, as he calls it, of site reliability engineering is to eliminate toil. I love toil. It's work that's manual, that's repetitive, that's tactile, that's devoid of enduring value, and that scales linearly as the service grows. Remember that. Something that scales linearly as a service grows has to go, because they had much bigger growth vision than scaling linearly. They wanted to pursue maximum change velocity without violating service level objectives. Lots of that is laid out in this book. And I'm going to talk about the second one, but I first want to talk about the first one. So if we go back to that same conference, Lattice, in 2008, and this was a keynote by James Hamilton, he talked about internet scale economics. So enterprise size data centers, you have an enterprise data center, you get about 1,000 servers. That time, 2008. You don't have those anymore, by the way, and you'll see why. The main cost is people, because you've got roughly 1 person per 1,000 servers, and the number of people grows linearly with servers. You get another 100 servers, you need another person. So the whole goal is to consolidate all the work onto fewer, larger systems. Now, see, I'm a queuing theory nut, so I don't believe in bigger, larger systems that batch everything, so that's pretty suspicious to me. And it became suspicious to a lot of other companies. When Amazon tried to consolidate everything onto a few larger servers, everything ground to halt, and they put on the brakes and went to a service-oriented architecture. Now, what Hamilton was talking about was internet scale installations are clusters of 1,000 servers. Okay, so they're basically clusters of enterprise data centers. Multiple clusters of 1,000 servers. Therefore, because they're not scaling linearly with people, the cost is 6 to 7 times lower than enterprise size installations. The main cost is the hardware itself and the power, and the people tend to be more like 5 to 10% of the total cost. Not really significant anymore. So therefore, in any internet scale environment, you want to scale out to multiple servers rather than up to great big computers. The mental model of this shift cost is pretty impressive. We want to do the same when we talk about microservices, scale out instead of scale up. Instead of a monolith, we need these little small things, because when you scale out, you can get really big. When you scale up, you reach a limit. So the idea is to replace lots of people with lots of software. And that's pretty much the story of what's gone on in the internet space and the microservices space these days. So let's go back to site reliability engineering. So you see all those people, they're only 5 to 10% of the overall cost. So you want them to be able to handle a very large number of servers. They're responsible for monitoring what's going on, and the monitoring systems that do it, for emergency response, for change management, so if you have to put in new routers or whatever, and for capacity planning. If you're going to get big fast, you need to be able to figure out how to grow, for availability, for latency, for performance, and for efficiency. So that's the job. But ultimately, you'll see this in the site reliability book. Site reliability engineering is there to optimize the user's overall happiness. I was at a conference of a very large retailer in Minnesota, and the head of their infrastructure and ops said to all of the people gathered there, which was his area, he says, we are the curators of our customers' happiness, of our customers' experience. So when you think about that, it's a pretty interesting way to look at it. one of the interesting things that Google talks about in the site reliability engineering book is this concept of an error budget. Because in the early days of Agile, we wanted to deploy all the time, fast. Yes, the data structures got in our way, but the other thing that got in our way were those guys in ops that every time we deployed, their pagers would go off that night because deployment meant problems. The problem between site reliability engineers and product teams, same problem between systems admins and product teams, is the systems admin, or the SRE's job, is to keep everything working right and never go down, and the job of the product teams is to run lots of experiments and learn really fast. So if you remember, if we go back to this particular slide, the third thing we're trying to do here is we're trying to pursue maximum change velocity without violating service level objectives. So the way they chose to do that, which is pretty interesting, is to have this concept of an error budget. What you're doing is establishing for any service a budget, which is going to be reliable enough. It's an agreement between SRE and the product teams, or the service teams, as to how much downtime you can tolerate in a quarter. Reliable enough. And in fact, you actually want to let the systems go down a bit, otherwise not much learning is going to take place. So there's a common incentive here between the site reliability engineers and the product teams to have the same thing happen, because here's what goes on. If I'm a product and I want to make a deploy, I can at will. None of those SREs are going to stop me or slow me down or give me any hassle, unless and until our team exceeds our quarterly error budget, at which time we don't get to deploy anymore. And then the SREs sort of have the say for the rest of the quarter as to how often if at all, we can deploy. So if you're within the error budget, you can do your new releases. If it's spent, you have to be either curtailed or done at the approval of the site reliability engineers. So what's going on here is that you have a tension that's being managed by this error budget, so that everybody is on the same sheet of music as to, yes, we want to go fast, but we don't want to go over this limit. So when it comes right down to it, reliable systems don't have to be perfect. They have to have sensible trade-offs, so that you can have the speed at the same time that you can have the reliability. And you need a mechanism to put sensible trade-offs in place that are pretty much automatic, not some engineering vice president coming down and saying, oh, you can't do that anymore. You need to have a sort of in the whole culture system to have that balance made. So this is one of my favorite SREs, site reliability engineers. I don't know if you know him. This is Mikey Dickerson. Mikey was very instrumental in October of 2013 in rescuing healthcare.gov. I know that doesn't mean a lot here, but it sure meant a lot in the US, where we were finally going to get a healthcare system that handled all of the different people in the country. And it was this massive software thing that took like 2 or 3 years to put together. And it was going to start up on October 1st, 2013. Bang, the whole country. Everybody could sign in that morning and log in and figure out how they were going to get their health insurance. Now, how well do you think that worked? Have you ever seen anything like that? I mean, the whole country, for heaven's sake. So I was sitting here thinking, sure. Well, Mikey is one of the guys and the leader of the team that was called by Todd Parks to come to Washington and fix it fast. Now, basically, everybody on the team had friends or relatives and everybody affected seriously by whether or not this piece of software got up and got running now. They all felt that it was very important for them, for their families, for the way that the whole country worked, to make sure this worked. And they came in as a team, and they figured out within days of how to get it started. Within a week, it was stabilized, and within 6 weeks, it was sort of pretty much working the way it was supposed to work. In almost every other case, that system would have been abandoned, 2 or 3 more years, and multiple billions of dollars more money spent to try and fix it. So that's a pretty impressive thing. This is how he talks about how site reliability engineers solve problems. He does a lot of sort of coaching and helping people think of what happens when things go wrong. So if something goes wrong and the system is down, all kinds of people are going to frantically look under every rock. They're going to find all kinds of things that are wrong. And how do you know what's the cause? So he says the best approach is to finding the cause is to pinpoint the moment in time when everything went wrong. So this is a picture that he posted on his blog or his Facebook page or something, and it looks like this. What happened to women in computer science? Now, I can't tell you how many times I've been asked this question, so I'll just put it up here. What happened to women in computer science? Because when I was in computer science, most, 50% or 40% of everybody I worked with was women. My two sisters, 1 year older and 1 year younger, were both programmers. What happened? And now if you take a look at that red line, that is computer science going into computer science as a major. What happened in 1984? So that's what he put out to the world. And somebody came back and said, here's what happened. But it happened in 1980, and that's the Commodore. And the Commodore became a toy for boys, not girls. And I read that, and I have a daughter. She was born in 1970, so she was 10 in 1980, and in 1984 she was 14. And I said, what do you think? She said, when I got to college, all of the boys in my entering class could program. None of the girls could because they didn't have toys at home. So they didn't bother to go into computer classes because they would look like they didn't know anything, and all the boys did. That's what happened. Parents didn't buy their daughters the same toys they bought their sons. Well, there might be other explanations, but that's my bet. Okay, so we saw this one before, so let's go on to this one. So what we're trying to do with Site Reliability Engineer is to take a bunch of really bad components and make them reliable. And there's a bunch of things you can do with architecture, but that only gets you 4 nines. Then you have to do partitioning to get you the rest of it. You decompose things into small services with decoupled deployment, monitoring, profiling, debugging, hooks at all levels. This is the kinds of things that SREs do. The general practices are heavily instrumented applications to detect failure, canary releases, failover to replicas, failover to other data centers, backend that are bad, you need to detect and isolate, easy to use defines, patterns, and abstractions for the applications programmers to use. But this role of putting all this stuff together didn't really exist 15 years ago. But today, there's a huge amount of work to be done in this area. Another really simple thing, yep, this is right, is, come on, let's go. Come on, there we go, chaos engineering. So this is a branch of site reliability engineering, a little bit of pioneering at Netflix. If you think about it, Neil Ford talked about fitness functions for architecture yesterday. Thought that was a real cool idea. This is in the Chaos Monkey that they designed at Netflix is sort of like a fitness function that operates in production against code to see whether or not it does the right thing when stuff goes wrong. In a little more graceful environment than if the system itself goes down. Corey, what's Corey's last name? He's on here. Rosenthal. Corey Rosenthal talks a lot about chaos engineering, and he was very instrumental in getting it started at Netflix. And he said, what you're trying to do with chaos engineering is run experiments to build confidence in the behavior and the reliability of the system. And the other thing you're trying to do is build expertise when emergencies happen, because emergencies do happen. So that's chaos engineering. And reliable systems become more reliable through this kind of work, through the work of SREs, through the work of chaos engineering, and through really making sure that the system over long term is stable. So, the question is this a cool job or not? Well, pros. You're responsible for the user experience. You're really close to users. Cons. You actually don't get to be responsible for product, if that happens to be your thing. Here's a big pro. In the US anyway, site reliability engineers entering the field earn 50% more than software engineers entering at the same point. That's a lot. So they're in high demand, and you have to be good to get the job, but should you get the job, it's a well-paying job. On the other hand, you're on call, usually day and night, so it can really dig into your regular life. It's got high demand for people, but it's a really demanding job. It's exhausting. And you have a lot of, lots of emergencies on your shoulders you have to do something about. It's an expanding new field, so if you like expanding new fields, this is a good one. It's got a kind of a fluid job description depending upon where you are, so what one person's SRE might not be the same as the other company's SRE jobs. Broad skills are required, so that's cool. On the other hand, because it's kind of fluid right now, the expertise you develop might not be as portable as if you happen to be in a different software engineering job. And there's significant autonomy. For those who do not like somebody giving them detailed tasks that they're supposed to do every day, and report in what did I do yesterday and what am I going to do tomorrow sort of stuff, for those who that's not real autonomy, this is a job where nobody's telling you what to do because nobody else has a clue. Just like when we did control systems, nobody told us what to do because nobody had a clue how to do control systems except us. And in SREs, nobody tells SREs what to do because the job is keep the site up and nobody else has a clue what to do. So you pretty much get to do what you and your team think is the right thing. No questions asked. Maybe a few cost questions, but not even those because a failure is pretty expensive. On the other hand, you have a significant exposure to being blamed for anything that goes wrong. So there you go, the pros and cons. So either this is your next job, or this is the job of somebody who you need to have as your best friend. So is this how much time is left, or how much time before questions? What? I can't hear you. Well, whatever. I'm just going to go through this and say thank you, and then we can do questions. How about that?
I have a question. On your slide, you said that parents were buying different toys for boys and girls. So my parents bought for me a ZX Spectrum, and at the age of 6, I had to learn BASIC just to play some stupid games. But that did not make me engineer. That made me a gamer. What's wrong with me?
So learning BASIC didn't make you an engineer, huh? Well, all I know is my daughter said that, she said, you didn't get Dustin, that's her brother, you didn't get him a computer either. Actually, we had computers in our house, but they were used for word processing because that was what computers were for kids, was to help them write better, and they did. But we didn't have computers as toys because they were what we used every day, both Tom and me, in our job. So that's not to say that every single toy is going to make a difference, but it is to say that in general, across a wide spectrum of kids, in that time frame, the 1980, 81, 82, when the Commodores came out, if there was a Commodore in the house, it was the boys, not the girls.
I guess I'm just an outlier. All right.
Not every house, probably not my house, actually. Do you think women will be back in computer science? If not, how to reestablish parity? Well, I think It's a fun job. It's just I just love the whole concept of engineering. And when the girls can do it when they're young, do things that show that this is a really fun, cool thing, then I expect maybe they'll like to do it when they grow up. So I have a little 4-year-old, my son, and their mother and father are both PhD, engineers, and she just loves programming. So they get her programming toys, she runs robots around. She might just be an engineer, who knows?
The lesson is here: buy computer-related toys to every kid, no matter boys or
by
girls.
the time kids are 12, it's too late. It is too late. This
Buy
is
for
something
your
that
kids.
has to be done when children are young. The idea of what you do when you grow up is established really, really young.
All right. We are all doomed. How do you stop senior management to overrule the safeguarding of SREs and forcing product team to deploy to achieve faster go-to-market times for features?
How do you stop senior management to overrule the safeguarding and forcing product team to deploy to chief? Oh, there are senior managers who do that?
All right.
They're crazy. So it's like there are always trade-offs, and trade-offs have to be made under some effective rules. If senior managers are making those level trade-offs down at the ground of what should and shouldn't be deployed, they have not done their job, because their job is to set up the environment and the rules so that the trade-offs are naturally made, okay? So the metrics are wrong. The way that people make trade-offs is wrong. They have not put on the ground the necessary rules so that the teams themselves can negotiate with each other and make trade-offs. So that's the problem there. How you make them change that problem, I don't know. But senior managers shouldn't be doing that sort of thing. They do, however, have a responsibility to make sure that the constraints and the objectives and the metrics are all in place so that good trade-offs can be made by the people way, way closer to the impact of those decisions.
All right. When should there be dedicated SRE roles, and when should product teams be their own SREs?
I think it's a matter of size, especially since data centers have now gone way into the cloud, but Netflix, had SREs even though they didn't really have data centers. So when there is a certain size and a certain mission critical nature to stuff being up and reliable, as opposed to it's not mission critical, I think there's a cutover there. It's a question you can ask of almost anything. When should architects have their own thing? When should we have a separate product thing? I like generally to see people doing pretty much one team does the whole thing. That's much more likely to find at Amazon. But actually, even there are SREs, because when you have this massive data center and it has all of these things, keeping it up and keeping it running is a really different engineering job than keeping the individual components and products working. So if you think about a big ship, okay, or a big building, it'll have a big power plant and a big boiler and all of that sort of stuff. There will be specialists in the different areas to make sure that all those systems that run that building are always up and running, or that run the ship are always up and running. And there will be a crew that focuses just on that. And there's good reason for that, because you don't ever want that ship to not have a power when it's out floating in the ocean because it crashes into rocks. So when it's really critical, you need to have people who are very, very skilled in that particular job and can react quickly, and to make sure that all the stuff is in place so that stuff doesn't go down. And when you have teams focusing on just making sure that we make product and delight customers and give them the features they want, give them the capabilities they want, that's maybe a whole different thought process. But I don't think there's a hard rule. I think it's a situational thing based on your business and your context.
All right. We are out of time, but because I'm nice, I'm gonna ask 2 more questions. So what happened around 2001? The decrease of women in computer science is even worse here.
I don't know. I didn't realize that there was a sharp drop in 2001. So I can't tell you the answer to that.
Probably some other technology was released and that was not bought for girls.
No, I really don't. I hadn't noticed the change, so I can't answer it. Sorry.
All right. The last one. With you build it, you run it, many companies expect normal engineers to be SREs as well. Is this the future, or did you think the two will by and large stay separate?
Okay, so let's go to AWS, that's where Werner Vogel first wrote that. You build it, you run it. That was his mantra for the service teams. They have SREs. It is true that there are ops people that are on the teams, but their data centers absolutely have SREs also. So let me look at this again. I definitely buy the you build it, you run it, but that doesn't mean I keep a data center up. It means if my service does something bad and messes up those guys' service and these guys' service, I'd better be ready to respond. But if the whole data center goes down because somebody pulls a plug on a router, it's not my problem. It's not actually any software team's problem, but it's got to be somebody's problem. And that's where the SREs have to step in. Because other things than my service causes problem happens. So there still has to be somebody that takes over when it's not an identifiable problem or it's just a fire or whatever else it takes to get the center back up.
All right, thank you so much for your performance.